Scanning electron microscope. A scanning electron microscope is a type of electron microscope that produces images of sample by scanning the surface with the focused beam of electrons. The electrons interact with atoms in the sample, producing various signals that contain information about the surface topography and composition of the sample. The electron beam is scanned in a raster scan pattern, and the position of the beam is combined with the intensity of the detected signals to produce an image. Principle. The principle of scanning electron microscope is the electrons interact with atoms in the sample, producing various signals that contain information about the surface topography and the composition of the sample. The accelerated electrons in SEM carry significant amount of kinetic energy, and this energy is dissipated as a variety of signals produced by electron sample interactions. Backscatter electrons are incidental electrons reflected backwards, which provide composition data related to the element and compound detection. Diffracted backscatter electrons determine crystalline structure as well as the orientation of minerals and microfabrics. X-ray emitted from beneath the sample surface can provide elements and mineral information. SEM produces black and white 3D images. Instrumentation of SEM. 1. Electron gun. It is a source of electron, typically a tungsten wire or field emission gun. Number 2. Condenser lens. It compresses the electron to a narrow beam. Number 3. Aperture. It controls the diameter of the electron beam. Number 4. Objective lens. It focuses the electron beam to the sample. Number 5. Sample chamber. This chamber keeps the sample or is simply the sample holder. Number 6. Detector. To detect the signals emitted. Number 5. Amplifier. To amplify the signals. And number 7. Display. To show the SEM image recorded/obtained. Construction of SEM. It consists of an electron gun to produce high energy electron beam. A magnetic condensing lens is used to condense the electron beam, and a scanning coil is arranged in between magnetic condensing lens and the sample. The electron detector is used to collect the secondary electrons and can be converted into electrical signals. These signals can be fed into CRO through video amplifier as shown.
Working of SEM. Stream of electrons are produced by the electron gun, and these primary electrons are accelerated by the grid and the anode. These accelerated primary electrons are made to be incident on the sample through condensing lenses and scanning coil. Working of SEM. Stream of electrons. These high-speed primary electrons, on falling over the sample, produces low-energy secondary electrons. The collection of secondary electrons are very difficult, and hence a high voltage is applied to the collector. These collected electrons produce scintillations onto the photo. Multiplied tubes are converted into electrical signals. These signals are amplified by the video amplifier and is fed to the CRO. By similar procedure, the electron beam scans from left to right, and the whole picture of the sample is obtained in the CRO screen.
Advantages of SEM or scanning electron microscope. Resolution. This test provides digital image resolution as low as 15 nanometers, providing instructive data for characterizing microstructures such as fracture, corrosion, grains, and grain boundaries. Traceable standard for magnification. Because all imaging is calibrated to a traceable standard, it's easy to apply analysis such as coating thickness, grain size determinations, and particle sizing to saved images. Instrument is very fast and easy to operate. Chemical analysis. SEM with EDS provides qualitative elemental analysis, standardless quantitative analysis, X-ray line scans, and mapping. This data can be used to examine product effects, identify the elemental composition of foreign materials, assess the thickness of coatings, and determine grain and particle size. Data is available in digital form. It gives 3D topographical images.
Disadvantages of scanning electron microscope. Number 1. Vacuum environment. In most cases, SEM samples must be solid and vacuum compatible. However, higher pressure can be used for imaging of vacuum sensitive samples that are non-conductive and volatile. Number 2. Instrument is expensive and large. Number 3. Risk of radiations associated with electrons. Number 4. Artifacts are possible, that is, samples that are strong insulators must be coated, usually with gold or carbon, before testing. However, this process can result in artifacts. That said, preparation and analysis by a knowledgeable SEM testing lab ensures that these artifacts have minimum impact on testing result. Number 5. Special training is required associated with electrons.
SEMs are used as very essential research tool in fields such as life science, biology, gemology, medical and forensic science and meteorology. SEMs are used in material science for research, quality control and failure analysis. SEMs are used to characterize nanowires and their gas sensing behavior. SEMs are used for a speedy, accurate measurement of the composition of semiconductors. SEMs are used for criminal and other forensic investigation. SEMs are used for geological sampling to determine weathering processes and morphology of the samples. SEMs are used in medical science to identify diseases, viruses, and testing new vaccination and medicines.